It's a great pleasure to have ROCIO TITIUNIK with us today. She's like a James Orin Murphy professor at the Department of Political Science. He's a methodologist, a political methodologist, interested in causal inference and especially in terms of the regression discontinuity design. Also with a substantive interest in political accountability. And I have to say, looking at her CV today, I realized that she's such a IDSS person, because you look like she has published in American Political Science Review, Econometrica, Journal of the Medical Statistical,
so can I get a
Association. Hoodie? Yeah. So these are kind of the, people will say the three best journals in economics, political science, and statistics. So not too bad. It's quite interdisciplinary, and we are super happy to have her here. And please join me in welcoming ROCIO TITIUNIK.
Thank you so much. You are too nice, Alberto. It's such an honor to be here. It really is. I'm delighted. Thank you so much for taking the time out of your busy, busy days to come to the talk. I will talk to you about regression discontinuity designs. I will call them RD, and that's the acronym. Over the last 8 years or so, depending how you want to count, I've been doing some work. A large part of my research agenda has been about RD methods, in particular about developing some methodological tools to improve the way in which we interpret and analyze the empirical evidence that comes out of this type of research designs. So before I go into the details, so the talk I prepared today, given the interdisciplinary nature of the audience, is an overview of the research design, and then some discussion of some recent research, and then another discussion connected to that is an overview of an ongoing project, all of which falls under the umbrella of methods for RD analysis. So I'll give you the details in a moment, but before, I kind of wanted to put the RD design into a larger context to give you my view and other people's views about how exactly the RD fits into a more general framework for thinking about causal inference and questions that we can answer in science. So it helps me to think about two types of scientific questions. The first type of scientific question is why? Why does an outcome or a phenomenon occur? So for example, why have far-right parties risen lately in democracies? Or why has allergy prevalence increased in the United States in the last 20 years? These are cause of effect questions. I see an effect, I ask what's the cause. Another type of question that we can ask is a more narrow type of question. So given that an outcome happens, we focus on one particular factor that might affect that outcome, and we ask, what is the effect of some cause, some treatment, some intervention on that outcome? So for example, what is the effect of winning a seat in parliament on the future electoral trajectory of the party, or what is the effect of exposing infants to allergens in their future allergy risk? So these are the kinds of questions that the so-called causal inference potential outcomes framework is focused on. And these are the type of questions that I will be focusing on. Ideally, science is at its best when the answers to these effective causes questions are actually informative about broader why questions in science. But I will be narrow today and focus in the latter. So causal inference framework, this is the question. What is the effect of treatment? So there's kind of a food chain here. I believe in MIT, everybody is familiar with a food chain. So at the very top of the food chain is a randomized controlled trial. So a researcher that randomly assigns the treatment or the intervention of interest really doesn't need to make any parametric assumptions to recover or identify, learn about the causal effect of this treatment. And so we consider this to be the gold standard. At the bottom of the food chain is a case where the researcher is not in control of the assignment of the treatment and also has no research design or any type of external thing in the world that helps with making any or justifying any of the assumptions. So everything here is assumption driven. Right? There's a middle. And in the middle is where almost in my entire research agenda lies, which is a situation which is a kind of a second best situation. So it's a situation where the researcher is not in control of the treatment assignment, but the researcher has a research design. And by this, I mean the researcher has some kind of external justification for the assumptions that, that he or she is going to impose. And these kind of assumptions are restrictions that we have to put on the data generating process that will allow us to identify a treatment effect. There are different types of things that we can do in this, in this middle area. We can have an auxiliary variable and call that an instrument. We can have a natural experiment and justify, some condition and covariates. We can have a time dimension and think about different synthetic controls. The RD design falls in there. So it's an observational study, a situation where the researcher doesn't control the treatment assignment. But one special feature about this design, which makes it, perhaps one of the most internally valid in this, second category, is that the assignment mechanism, the way in which the treatment is assigned, is known. And this gives us a really good basis, objective basis, to evaluate how plausible the assumptions that we need for identification are. All of these designs here make untestable assumptions, but some are better than others in providing some ways of actually evaluating how plausible this might be. So what is the RD design? So that's the context. What is it? Well, it's defined by three things: a score, a cutoff, and a treatment. You have an RD design if all the units in your study receive a score, and if you assign a treatment based on the following rule. All the units that have score above a cutoff get the treated, and all the units that have score below the cutoff get a control. So what you have here comes from a real paper. So here I have on the x-axis a score, and on the y-axis I have the probability of receiving treatment conditional on the score. So this example is coming from an actual paper. So New York public schools record height and weight for all their students. Using height and weight, they calculate BMI index. So BMI index is weight over height squared. So it's an adjusted measure of your weight adjusted by your height. And then there are cutoffs that come from the medical community that say if your BMI, body mass index, is above a cutoff, we are considered overweight. And if it's below a cutoff, you're considered healthy weight. In New York public schools, they, using the cutoffs, they classify children according to whether they were overweight or not. And then for those who were above the cutoff, they reported in their report cards, your child is overweight. And for those who were below the cutoff, they didn't. And so there's a literature in psychology that is interested about the stigma of being told that you're overweight, whether that has psychological effects. And there's also people who are interested in the possibly detrimental effects that dieting has on future weight. And so they're interested in whether receiving the treatment of being labeled as overweight actually affects their future performance. Now, if you're interested in the treatment of being labeled overweight or not, if you compare, so people here are very overweight and people here are healthy weight and underweight. Obviously, comparing people that are very different in terms of their body mass index implies that you're comparing very different type of people. And if you look at their future weight outcomes, then they're going to differ in a lot of ways because they probably have different, massively different habits. But if you look right around the cutoff, then you're going to be comparing two students that essentially have the same weight, except for some random noise, right? Some very small variation that due to whatever they ate that morning when they were weight. And so essentially, you will be comparing people who are right above it. You're going to be comparing with people who are right below it. They have essentially the same weight. They're only different in that they've been labeled healthy weight or overweight. So what you see here is that having this rule in the treatment assignment creates an abrupt change in the probability of receiving treatment. So if you're below the cutoff, your probability of receiving treatment is 0. If you're above the cutoff, your probability of receiving treatment, in this case, is 1. And this is called a sharp RD. It could be less than 1, but we're going to focus on a case where it's 1. So the rest of the talk, I will define the parameter of interest, talk very briefly about identification, which is not what I'm concerned here today. This is a prior result. And then I'm going to talk about how do we make inference that is robust based on local polynomials once we have an RD design and we have identified the parameter of interest. And then I'm going to move on to a key open question that remains. So this is more recent, like ongoing research, which focuses more on the limitations of one of the main limitations of the design that I'll talk about, and how to try to overcome that. And then there's a lot of stuff that I will not talk about. maybe we can talk about in the Q&A or later or by email, or I prefer no email. Maybe call me because I get too many emails. But by phone call or by, we can talk about all, other things that I've been working on the RD design, geographic, local randomization, and discrete random variables. So these are the basics. Very simple notation. We're going to keep it very simple. I'm going to assume I have n units in the study, I through 1 through n. X is going to be the score. There's going to be a treatment. It's just an indicator function for whether the value of your score, of your BMI index, is above the cutoff. The cutoff is going to be x0. And I'm going to adopt the potential outcomes framework. So I'm going to say y1 is the outcome that I see if you receive the treatment, and y0 is the outcome that I see if you receive control. And I'm interested in the difference between y1 and y0, which is a way to capture the treatment effect. These two outcomes are potential, but a single unit only either receives the treatment or the control, so I do not get to observe both of them for the same unit, and that's the famous fundamental problem of causal inference. Let me show you this picture, which I'm going to be showing you over and over, because one of the nice things about the RD is that you can explain it to your mother with a picture, or father. It's true. My father wouldn't be interested. I think that's why I chose mother. So this picture has the score on the x-axis. And on the y-axis, it has just the conditional expectation of the potential outcome under treatment or under control given the score. So that's a regression function. What I have plotted here is these two regression functions, the expectation of the potential outcome under treatment given the score, and the potential outcome of the conditional expectation of the potential outcome under control given the score. And this is the outcome of interest. So in the effect, in the case of being labeled overweight versus not, you can measure the outcome could be, did you diet in the last 3 months? Yes or no? So we are interested in the difference between these two curves, right? The average treatment effect at any point is the vertical distance between these two curves. If we could observe them both, we would just go ahead and, compute the difference at every point and integrate over, take an overall average, either calculate the average treatment effect at a given point or the overall average treatment effect. But the problem is the fundamental problem of causal inference means I don't get to observe, right? This curve, which is the regression function of the control group, I don't get to observe it. If you're above the cutoff, you're treated, so I don't know what would have happened to you if you hadn't been treated, and vice versa. So the entire average treatment effect, it's really, the vertical distance is unavailable except at the point of the cutoff. This is a very special point where we almost get to observe the vertical distance, right? And so we define this as the parameter of interest in the regression discontinuity design, not because we're interested in it. It's because the only thing that we can get. And that's the second part of the talk. If I get to it, is, that's a big weakness, okay? But bear with me. This is the parameter of interest, which is right there. Is the average treatment effect right at the cutoff. And the identification result says that if you assume that these regression functions are continuous around the cutoff, then I can take the limit of the observed function from below the cutoff, and then the limit from the treated function from above the cutoff, and the difference of those two limits, both of which are observable, right, and can be estimated, that difference that depends on observable variables is equal to the unobservable jump in the in that conditional expectation. So we can identify the average treatment effect at the cutoff. And that's going to be, from now on, our parameter of interest, right? This result is due to Hantot and van der Cloud, 2001. So this is, well known. So what I want to talk about, yes, go ahead.
So, if you showed me this picture and asked me how I should separate the sets, I'd say I should alternate 1, 2, 1, and then so I can fit my regression functions better. So
separate them what? How?
So say take the first person and don't give treatment, take second person, give them the treatment, and so on.
Oh.
So I'd have points evenly spaced along the line. So
yeah.
my curves would be.
Yeah.
Okay. Sorry. I guess I have the end of my question.
So I can. You want me to repeat the question, or you can ask it again?
Yeah, you're welcome to repeat.
No, you can go if you have the. That's your question.
Justify my microphone. Okay. I'm saying that instead of separating it into the first half and the second half,
yeah.
If you showed me a picture like this, my first thing would be to take, say, the lightest person and don't give them the treatment, and the second lightest, and then give them the treatment.
Alternate.
And alternate, exactly.
Yeah.
So that when I do this fitting, I'd have, more points right along the curve to fit. So
yeah.
what would be the intuition behind splitting it up this way instead?
Yeah, no. I don't want this either. I don't want this either. But remember, it's here. I didn't assign this intervention. If I could assign it myself, I absolutely wouldn't do it in this way, because precisely for what you say, right? Because why would I do it in this way? Then I can only focus on the effect right at the point where, but I could either alternate, or how about this? I could randomly assign them to one group or the other. The point is, the RD design happens, and we are going to use it for our benefit. But the person who did it is a policymaker who couldn't care less about causal inference or science.
Oftentimes policymakers will assign things in this.
Absolutely. For example, I'll give you an example. Poverty alleviation programs, they often rank municipalities or districts or even households from the most poor to the least poor, and they start giving assistance to the most poor, and they stop giving it as soon as they run out of money. And that's your cutoff. And they do it in that way because alternating there wouldn't make sense, or randomly assign it would make sense for us scientists, but it wouldn't be fair, because we would give in resources to people who don't need it. And so a lot of needs-based programs are assigned in this way. And so, yeah, that's the answer.
But it's also related to the idea that we all often think about the regression discontinuity design as a like a non-experimental design, but it could be an experimental, non-randomized design. You may want to do an experiment. You may not be able to do a randomized experiment because many limitations, political reasons, and you may want to impose this against on identification.
Yes, if you couldn't randomize.
If you could not randomize.
Yeah, I wouldn't do it if I could randomize.
Yeah, but not always you can randomize.
No, absolutely. If you talk to a policymaker and you say, let me randomize, they look at you like you just came from a planet they cannot understand, because that doesn't seem, the notion of fairness. I mean, try to explain to my kids that randomization is fair. They don't agree with that. So absolutely. So it's basically, it's not under our control. Okay, so when I have, it has become kind of standard to use a particular kind of method, which is local polynomials, to estimate this treatment effect. So I'm going to now describe how to do local polynomial to estimate this effect, assuming that this is the effect that we are interested in. And then we're going to discuss how to make inference, and I'll tell you about some results about it. So I'm going to choose a polynomial, a bandwidth, and a kernel. I'd rather explain it to you with pictures. So imagine that I have, this is the truth. So these are the two regression functions that I don't get to see, but we get to do this experiment. And now I get data from it, right? And then when I receive it and it's in my computer, I don't get to see the actual functions behind my data. I just see the data, right? So this is what we get to see. And now, so how local polynomial estimation proceeds is, well, so what we know is we have all these data points. We know the score and we know the cutoff. The cutoff is known, right, by us. And we know that the treatment was assigned according to the regression discontinuity rule. So we are only interested in the jump. Well, we can only identify. Therefore, we're only interested in the average treatment effect of the cutoff. So what we're going to do is local polynomial estimation, which means we're going to fit a polynomial close to the cutoff. So the first thing we do, is maybe we are going to weigh the observations using a kernel to give more weight to observations that are close and they're farther away. And then I'm going to choose a bandwidth. And I'll talk a little bit more about how to choose bandwidth. So a bandwidth, what it's going to do is going to localize. So it's going to kind of drop observations that are aside so that I focus only on observations that are very close to the cutoff, because I don't want my estimation to be influenced by observations that are too far away, because I'm not interested in the far away anyway. There's nothing that I can identify far away from the cutoff anyway. And then if I'm doing local linear polynomials, so if I'm doing a polynomial of order 1, I'm just fitting a linear regression on one side, and then I fit another on the other side separately. These are separate regressions. So I'm only using the treated sample here, and I'm only using the control sample here. And then I take the estimated intercept and take the difference. And the hope is that that estimated jump is actually very close to the actual, the actual parameter. And it is, under some conditions, that's a consistent estimator. And this is a good way to do things. So the question that we have studied is, given these steps, how are we going to make inference about this parameter? So the steps are as follows. So you choose an order of the polynomial. So in the example I just showed you, it was linear. So just a linear function. And then we choose typically a kernel function to weight observations, though you could choose not to weigh. And then given that order of the polynomial, we choose a bandwidth. A method to choose the bandwidth that has become preferred by a lot of practitioners is to choose a bandwidth that is mean square error optimal. And what that means is it's the bandwidth that minimizes the approximation to the asymptotic mean square error of the point estimator. So if you think about this point estimator here has a mean square error, asymptotic mean square error, we can approximate that. That mean square error depends on the bandwidth, and I can choose the bandwidth optimally given the order of the polynomial so that that mean square error is minimized. That's what that's the MSC. Well, that's what MSC means. So mean square error optimal bandwidth, and you can show that the bandwidth depends on the sample size and a constant is trading off variance and bias, right? So the more variability I have, the wider the bandwidth is going to be to control the variance because I need more observations. But the more the bias is a concern, the smaller the bandwidth is going to be because the smaller the bandwidth, the better the approximation. Okay. Given the order of the polynomial. So the question is, if you choose a polynomial and then a bandwidth that is optimal in this way, if you build a point estimator, then we know that this point estimator is going to be consistent and optimal and so on. The question is, given those steps, how do we make inferences about this parameter? By that I mean, how do we build confidence intervals that are valid? And so if you think about it, all we're doing practically, and if you're a social scientist, this will be very obvious, but maybe not if you're not, is just fitting a least squares regression on either side of the cutoff. So this is very popular in social science. And so one temptation would be to just build the usual t statistic, right, where we just take the difference, the estimated intercept and divide it by the square root of the variance, and we just use a standard normal approximation, which would come from conventional least squares inference. So we would build a confidence interval, just your usual point estimator plus minus 196 times square root of the variance. Now, this is where things get interesting. So the thing about doing inference as your usual least squares inference is that there's a difference between running a polynomial that it's the true model and running a polynomial and fitting a polynomial as an approximation to an unknown function. And so what you can show is that with appropriate rate restrictions is that t statistic where now, which that t statistic, the usual point estimator divided by the standard error, it is normally distributed converges in distribution to a normal, but it's not really centered at 0. It has a bias. And the bias, what is the bias? The bias is an error. It's the error that we have introduced in the approximation. So the error is coming from the fact that I chose a linear polynomial or any polynomial of any order to approximate an unknown regression function that is most likely not exactly equal to a polynomial of that order. So there's a misspecification error there. And in the general case, the misspecification error means that the distribution that you should use to build your critical values, to build your confidence intervals, is actually not centered at 0. It's centered at that error. So what do you need to assume to use your conventional confidence interval that just uses the standard normal? Well, you have to assume that either your polynomial is exactly the true functional form, or that your bias goes to 0 very quickly. And if it does, then that bias kind of disappears, and it doesn't appear in the distributional approximation. So we call this the undersmoothing. So the thing about this is that if you remember the mean square or optimal bandwidth, you can show that if you pick the bandwidth according to the mean square or optimal criterion, that bandwidth is such that if that bias is non-zero, that bias is guaranteed to show up in the distributional approximation. So if the bias is non-zero, the mean square or optimal bandwidth implies that these confidence intervals are always invalid. Right? So if you want these confidence intervals to be valid, you will need to get that bandwidth that is optimal and then make it smaller. And that's what we call by undersmoothing. And then this might become valid. So what's an alternative? An alternative is to go ahead and estimate this bias. And this is like a technique that's called bias correction that is quite common. So what we can do is we estimate the bias and manually remove it from the point estimator, and then build this confidence interval. And this bias correction approach is valid and gives you asymptotically valid confidence intervals. But the issue with this approach is that it doesn't really work in finite samples very well. And applied researchers who use this can tell you. And the reason is that these confidence intervals are derived under the assumption that this bias estimation step doesn't contribute to the variability at all. So whatever variability we introduce when we estimate this additional term, we assume the rate restrictions that are assumed here imply that that additional variability disappears, right? And it doesn't show up in the distributional approximation. So it's kind of this approach. So if you imagine you have the bias-corrected test statistic. So this is the point estimator. This is an estimated bias, which is going to depend on, you can also estimate with local polynomials. Divided by the standard error, you can kind of add and subtract and write it as the product of these two studentized test statistic. And so this is the bias, this bias-corrected statistic converges to a standard normal. The standard approach of bias correction is to assume conditions such that this thing converges in probability to 0. Right? What we do in our robust inference paper is to use non-standard asymptotics, which is an agenda of some proportion of our co-authors, not me. And in these non-standard asymptotics, what we do is to say, well, instead of imposing these conditions, as people who do asymptotic theory, they're like magicians, right? You tell them what you want, and they give you the rates that you need to get what you want. It's awesome. And then the question is whether this works in your finite sample, and that's where that reality hits. So what happens here is that in non-standard asymptotics, instead of assuming that this thing converges in probability to 0, to a constant, we relax those restrictions and let this converge to a random variable. And so what happens is that when you do that, you let this term capture the additional variability that you introduce by estimating the bias. And so from here, you can derive what we call robust bias corrected. So they're bias corrected, and they have an additional term in the variance that accounts from the variability that you introduced in the bias correction step. And the thing about these confidence intervals is that they allow you to use for inference the same bandwidth that you use for point estimation. So that means square optimal bandwidth. And they also have very, very good finite sample properties, much better than your typical bias correction Because if you compare them here, now you can compare the three of them. In the conventional confidence interval, you assume that there is no misspecification error of any kind. So basically, the model that you're doing is a parametric model. In the bias correction, you admit, right, that this is an approximation and there's an error. You estimate it, but you leave the variance estimator unchanged. And this you can use with this you cannot use with the mean square optimal bandwidth. So these are invalid. This you can, but they have very bad coverage in practice because this variability here pretends like you never estimated the bias. It pretends like you knew it, right? But you just replace an unknown quantity with an estimator of it and just left the variance estimator unchanged. Our robust confidence intervals use this non-standard asymptotic to modify the variance estimator to incorporate the variability that we introduced by doing the bias correction. And so what we have are confidence intervals that actually work a lot better. And the interesting thing about them, I don't know, the way I learned about hypothesis testing was by studying Fisherian inference. And in Fisherian inference, hypothesis testing is not at all tied to point estimation. It's a completely separate concept. You actually talk about testing of hypotheses without ever talking about point estimators. The thing about these robust confidence intervals is that they require you to kind of think about point estimation as a completely separate concept from doing inference, because those still the object of interest, your point estimator that is mean square or optimal, is this tau hat, which is that estimated jump of the regression functions. But if you look at the confidence interval, the confidence interval is not centered at that point estimate. Yes?
There is another option, right, that you can use. You can calculate the mean square error minimizing bandwidth and then use local quadratic regression. Increase the order of the polynomial, you under smooth it that way.
Yes.
So
there is actually an equivalence.
Yeah, and it's an equivalent with higher order kernels.
Do I do this or not?
No. Yes, because I saw the list of things. I think that there may be one more.
Well, I can tell you an equivalence between, so what you just said. So we can show that if you estimate the mean square optimal bandwidth for p equal to 1, and then in that bandwidth, you do our bias correction with p equal to 2, the conventional confidence intervals with p equal to 2 are equal to the confidence intervals that you would get. The robust confidence intervals that you would get with p equal to 1 are equal to the conventional confidence intervals that you would get in the mean square optimal bandwidth with p equal to 2. Did you follow what I said? So if you give me the mean square, so if you give me the 8 mean square error, and you estimate the mean square optimal bandwidth for p equal 1, yeah. And now you estimate, you go to this bandwidth and you estimate with p equal to 2, yeah. And construct the conventional confidence intervals. Those are equivalent to go to p equal 1 and do robust.
Yeah, so that's what I was saying.
Yes.
Instead of doing this, you could do the first.
Yes. And so exactly. So there's an equivalence there that is an exact equivalence if the bandwidth that you use for the bias is the same as h. But
and is any advantage one or the other in a higher order?
Robust bias correction is, and so Farrell, Cattaneo, and Kaloniko, I think, is in that paper. They actually show that this has higher order refinements that an undersmoothing, yeah, that doesn't have. So it's preferable. How are we doing on time? Oh, 20 minutes. So I have an empirical application. I'll go over this very quickly. I just wanted to show you that, I also do it for real. This is how it all started, actually. So here I have a question that is of interest to some subset of political scientists, myself included. the question is whether when a party wins, I keep doing that. When the party wins an election and becomes an incumbent party, does that in and of itself give the party an advantage in the future? Right? So the fact that you get to office today, does that shield you from future challengers? Is that beneficial? And so what you can do, and an economist first thought about this, is we can think about, imagine you have only two parties, 50% of the vote becomes the cutoff for deciding who wins and who loses. And so what we can do is here I have a regression discontinuity design with the vote share that the Democratic Party gets in one election, and this is US Senate elections. And it's the margin of victory. So if the margin of victory is positive, the Democratic Party wins a Senate election. If the margin is negative, it loses the election. And the y-axis here are the vote share that the Democratic Party gets in the following election for the same seat in the Senate. And so what you see is there's a positive slope, which is understandable, expected. Places where Democrats get 80% of the vote yesterday, they tend to get 80% of the vote tomorrow. And so there's a positive relationship, as you would expect. But right around the cutoff, there seems to be a big jump, right? So that in races where Democrats barely lose, compared to places where they barely win, they suffer, right? By barely winning, basically they win about, it's like a 7 percentage point or 8 percentage point boost, in a similar, otherwise similar, the assumption is, right, otherwise similar race. And so here is what you would do, like you would fit, like we have software that implements all these methods, and the way we would fit it is, well, we have our ROCIO package, but really the way you can fit it is you estimate the bandwidth, and then you can even do this manually, right? And I do this for teaching, where you just build one fit on the right, one fit on the left, and take the difference between those. And so what I wanted to show you here is that the way you can see how the theory maps into the empirical results. Because here you have the conventional point estimator. That's the simple difference in those estimated intercepts. And this is the conventional standard error and the conventional confidence intervals that you would build with the usual LS. This assumes that your model is correctly specified, no error. Here we have the bias corrected statistic, which is different, right? Because here we have estimated the bias, subtracted it. And the confidence intervals here don't adjust for the standard error. So if you look at the standard error, this one is the same as the conventional. Our confidence intervals are centered around the bias corrected point estimator. They use these new standard errors that are higher. They will be higher because they incorporate this additional variability, and then they produce these confidence intervals that slightly wider and they're longer in length. And these are asymptotic about it. In this particular case, it doesn't change the conclusion that the effect is significantly different from 0. But this is how you can see the mapping between the actual data and the theory. So this is one kind of quick overview of what it takes. This is, in a way, this is how it all started. We were analyzing these RD designs back in the day when we didn't understand very well how to, so we were just running simple parametric models and doing inference, and the question was, is this really okay, what we're doing? And so we kind of went into it, and many years later we emerged with some understanding, so I'm happy about that. So I feel we have a good grasp now on if you want to use local polynomial methods and you build, how to do valid inference. How also, I haven't talked about, but we also have a decent understanding of how to do falsification of some of these untestable assumptions, what kind of evidence you have to present for convincing your audience that the RD is valid. But one of the things that is really a weakness of the design is what I said in the beginning. This parameter of interest, is that really what we were interested in, or is it not? And another way of asking is how much external validity does this, does this effect have? So sure, this is the RD treatment effect, and we all write a lot of papers trying to make valid inferences for that parameter and so on. But really, honestly, I'm interested about the average treatment effect, for everybody or in all points of the support. And so what can we say about, the average treatment effect in other places? And so you might imagine a world where the vertical distance between the two regression functions is constant. So once you know what the distance is, once you know the effect at the cutoff, you know the effect everywhere. So if you think that the world behaves more or less in that way, you'd be very happy to have one RD design, because really you could say, look, I have evidence from this RD design, and I believe that the world is more or less, constant treatment effect world, and so I can use this effect at the cutoff to inform, what I think the effect is in other places. But sometimes, the world is heterogeneous, right? So such that the effect that you see at the cutoff might not be the effect that you see in other places. And so this could be a case of mild heterogeneity. But the world could also be, so the problem with mild heterogeneity, this is still OK. You might say, look, the effect is positive, and it's positive everywhere. So it won't mislead you too much. But if your heterogeneity is like this, you might conclude that this policy is very effective. And when it is effective here for these units, but it's very ineffective at the extremes, right? Yes?
It's just a clarification. So it seems to me that this gap that you're describing is somewhat exaggerated, in the sense that I think that if we go back to your BMI example,
yeah.
If you have an intervention for the epsilon larger than the cutoff, you essentially bring them to the cutoff. And so this curve looks, the jump looks very close to zero, the benefit.
No, so there are two jumps that are going on. Let me go back, can I? There are two jumps that are going on. One is a jump in the probability of receiving treatment.
That's 0, 1.
That's 0, 1. And that's the jump that's the jump that is guaranteed by design. The other jump, it depends on what the treatment effect is. And so, but the design has no relationship to that.
Right, but I'm saying that in practical situations, I don't expect that the treatment will transfer somebody the benefit of the treatment would be that large if you're that far away from the cutoff. In the sense that what's deemed acceptable after treatment would be to shift below the threshold. So if you're overweight, you're not going to lose.
No. Okay, but let me change the outcome. So yeah, if the outcome is weight, I agree with you. Yeah. But that's a very specific case because the score and the outcome are almost the same thing. Yeah. But think that the outcome is psychological. It's like some psychological test of how stressed out you are, or your body image, your self-esteem.
Or weight in the future.
Yeah, or weight next year, or next 6 months. Yeah, that was my bad, actually. That's a good point about that example. Those outcomes happen to be very related, but that's not a feature of the design. That's just that particular example. Mm-hmm. OK, so I want to leave some time for even more questions. The one project that we have in mind, so how to increase how to say something about the effect in other parts of the support is the big open question, right, in the RD literature. We have a good understanding of how to, estimate and do inference for this effect, but really, how can we use this design to say something more general? That's the big open questions. There's several papers that try to make, there's no free lunch. We have to make additional assumptions. Otherwise, we're not going to be able to say anything. Here's one idea that we have. And this is one project that is ongoing. In practice, even the BMI example and even the party example, in practice, there's a lot of RD designs where the different subsets of units actually see different values of the cutoff, right? So your classification for overweight depends on actually how old you are. If you're 9, it's 20.2, I think, but if you're 10, it's 20.3. And these are different examples from social assistance programs that in different geographic regions, because they have different socioeconomic characteristics, they use different cutoffs, right? So an RD with multiple cutoffs looks like something like this. You have the score, you have C0, it's missing, and C1. And so you have one cutoff, and this population in blue here is exposed to this cutoff. And then you have another cutoff that actually affects a different population, right? They're all part of your RD design. Typically, what people do is they normalize, and they analyze them all jointly. Nothing wrong with that. That's fine. But the idea that we have is, oh, OK, but wait a minute. If you look at this, when I have multiple cutoffs, I have a special, I have this situation where for these values of the cutoff, I actually see the two populations, the two control populations. I can observe their outcome under control for both populations. Now, once I cross the first cutoff, I no longer observe the control outcomes for this population, but I continue to observe this one. And so the idea that we have is, well, imagine that now, so I can definitely identify and estimate using a robust inference method and so on. I can estimate those two effects here. I can do that. But what if we're interested in extrapolation? What does extrapolation mean? Well, it means that I might be interested in this effect. What is the effect for the population exposed to the low cutoff at a point that is higher, right? Such as this one. And so one idea that we have is to concentrate on this difference. So if you define, this is our treatment of interest, but we don't get to observe this because we don't observe this line because everybody past this point is treated, but we have controls here. So one naive thing would be to compare this treatment group to the other control group. That's naive because these regression functions are not the same. But the idea that we had was, well, but we don't observe the two control groups here, but we observe them a little bit, before. A little bit depends, up to you. You could, choose to estimate this, this extrapolation effect even closer. And so the idea is to, if we assume that the difference that we call the bias, like the difference in the control groups stays constant as I move along the score, then I could estimate it here and then subtract it. So then this is an observable jump, and this is also an observable jump. And so under the assumption that the bias stays constant, I can subtract from this naive difference the bias when the difference between the control groups and identify the extrapolated effect. If you're familiar with difference in difference designs, this is has the same flavor. How believable this is going to be very application specific. Perhaps it will also depend on how far you go away from the point where you can measure the difference, right? So there's going to be a tension perhaps between how plausible this constant assumption is going to be and how far out you're going to go. In an era of big data, this actually might be good. I mean, might be actually feasible. I think 20 years ago, people would have said, that's great, but completely impractical because I will never have enough observations to actually estimate nonparametrically all the objects that I need to do this. But now I think it's actually a different world where we would actually have a lot of applications where we actually have data to implement this. So that's kind of where we're going. It's probably going to be one of our last projects in the agenda. I have an empirical application, but I really want to leave time for questions. Happy to show, to show you more about it. But I hope that I gave you a little bit of a flavor of what, the research agenda has been, what the RD design is, how it's very important to take it very seriously and try to do inferences and falsification and take every particular RD design very seriously, but at the same time, what we're trying to do now and other people are also trying to do is how to think more broadly about extrapolation and how to think about more general questions and more general parameters. Because that parameter was not decided by us, right? So it's something that we're worried about. Okay, so I think there's a few minutes.
Do you have an example where the robust confidence interval actually overturns like a finding? Yeah.
But I'm not going to name any names. Yes. it happens. If you think about what's happening with the robust confidence intervals, so let's say these are the conventional ones. So the robust confidence interval, it's going to be wider. If it were centered at the same point and wider, no one would use them, because guess what? It would always make it harder to reject the null. But lucky for us, the robust confidence intervals, they're not only rescaled, they're recentered. So sometimes they're recentered in a way that, so they're wider, but they go like this. And so if this is 0 over here, when they move, if the conventional confidence interval had a p-value, say, very, very close to 0.05, and the bias is such that the interval moves a little bit to the left, then you lose statistical significance. But it could also move further to the right. So yes, it can go either way. It can go either way, and it depends on that.
So, when we should be more worried or less worried?
Yeah, so the bias is related to the curvature of the regression functions. So if your regression functions have a lot of curvature, and you did conventional confidence intervals, you had a lot of bias and you essentially ignored it. And so when you use robust, you're going to account for that bias. And so that point estimate, the bias corrected point estimator is actually going to be different from the non-bias corrected one. And that's when it's going to be more likely that the inference will change. Yeah.
Applications where there are legal ages for something.
Legal ages, yes, like voting.
Or drinking or anything. So I suspect that there might be a lot of fake data exactly at the intersection.
Absolutely.
So, because for obvious reasons. So are there standard methods to purify the data?
Yeah, I like this term very much, purify. Yes, so the problem that you're referring to in the literature of RD is usually called as sorting around the cutoff. There are some methods that have been developed to test some empirical implications. So that's an unobservable thing that we have to assume that doesn't happen. But there are two things that we can do. One, if people are, if people really desire this treatment, and they, like say drinking, and so if they're if you think that people who are very close to the cutoff, but are going to benefit a lot from the treatment, have an incentive to actually fake their score and jump to the other side, then that benefit from treatment, which should give you the incentive to change your score, should probably correlate with other characteristics of you. And so so for example, one example I use is sometimes, let's say, I have a program in school, and I choose to give this program to kids who are, I give a recognition, or I give an award or some kind of, thing to kids. Let's say there's a cutoff based on performance in the classroom, and I give an award to everybody above the cutoff. If your kid is very close to the cutoff, there are two types of mothers. Mothers who will say, oh, bad luck. And then there's the type of mother who will go talk to the principal, right? And guess what? The type of mother that goes to talk to the principal tends to be more educated, have more flexible job, right? And be, and have higher socioeconomic characteristics. So if in your data you have these characteristics of your units, you can test whether around the cutoff you observe a jump in the characteristics of your units. If your story about sorting is true, you should see it in some pattern. So you should see that you should say, this is very strange. Even though this is supposed to be completely arbitrary, I find that, of the units right above the cutoff, 80% of those mothers have PhDs, and only 20 on the other side. And you go, okay, I don't believe this design anymore. Okay. And then another method is to look at whether the number of observations jumps, the density, whether instead of having balanced observations above and below, you have a very big jump, so that all of a sudden, a few points before the treatment, there's no more controls and everybody's treated on the other side. That's another method. So absolutely, that's the #1 concern, because we are dealing, these are human beings typically that we study with RD designs. And as we know, humans do this kind of thing.
So this corrective term that you put in the variance, if you use a higher order polynomial, does that go to 0?
So this is this corrective term, the bias. So there are two things going on, right? So two things. One is we bias correct, and we adjust the variance for this. If you increase the order of the polynomial, you control bias better, and so this coefficient is going to be smaller and smaller because your higher order polynomial will be a better approximation. Your error will shrink. You will always be introducing increased variance, though, because even when this is 0 and you're estimating, you're introducing noise.
Thank you. So we talked a lot about this robust inference under bias correction. And I found this extrapolation discussion at the very end really, really exciting.
Yeah.
And I got the intuition for the difference in differences and parallel trend assumption kicking in this case. I'm having a hard time trying to, so I was thinking about like being a magician, like trying to do the robust inference in this case.
Yeah.
Not only need to make an assumption about the some sort of parallel trends across the different completely different populations, but also we need to think a little bit about the differences in the variability in those two different populations in terms of making a robust inference. So I'm just curious whether you have thought about that, and if so, if there's any intuition about how to.
Well, absolutely we have. Absolutely, there are more things to estimate here. And the way which we're thinking about estimation is, again, by using local polynomials and doing inference that is robust. One thing that we are kind of developing as part of this project is you could do an inference that is joint, like sort of estimate all of these things together at the same time and gain some efficiency in there. But every single one of these effects, so this one here, this one on the other cutoff, and these points, we can estimate with local polynomials, and we can use the bias correction ideas and do robust inference for every one of them. The only difference is this is a boundary point. This one is not. So that changes a little bit of the kind of tools that are available. But other than that, kind of the same ideas. In terms of estimation and inference, there's really not much of a difference, except that we're doing more of it, like at more different points. You see what I mean? So the parallel trends assumption is more about identification than about inference.
We are done with the seminar, but we are going to have a reception right now as you go out to the left, and I'm sure that Professor TITIUNIK will be happy to address many more questions. But now, we should finish with the seminar, and please join me in thanking.